So for any relative velocity question, whether it's in one dimension or two dimension, I always would start off with a diagram because that is going to frame your reference point clearly. So for this question in particular, we can say that the distance between each of the river or side of the river banks, I should say, so the south bank and the north bank would be 200 meters wide. And then we draw the current going east and the swimmer going north. Now there's two ultimate reference points that we can observe the speed of the swimmer. One would be the speed relative to the water. And when we mention a speed that is in still water, normally that would be the maximum speed, but that's when it's relative to the actual water. The other reference point would be from the bank, right? So an observer looking at the swimmer from the opposite side of the river. So in this case, when it's relative to the river bank, the observer is going to see the speed, remember not the velocity, but the speed of the swimmer going north and being pushed to the side by the current. So they'll see the hypotenuse level of the speed. This means that the 1.8 meters per second relative to the bank won't be the max speed in our vector triangle. Relative to the riverbank, the max speed will be a combined speed of the swimmer in still water and the current that is interfering with that still water speed. That being said, when we draw our vector diagram here, that means that the 1.8 meters per second for the swimmer in still water is going to be our y vector, and then the current going east will be our x vector. And then the resultant, remember that this is the speed that the observer on the other side of the bank would see, would be our hypotenuse. So using Pythagorean theorem, we're going to solve for the resultant vector. And again, this speed would represent the magnitude of the speed that the observer would be witnessing. So sort of the speed or how fast the swimmer would be going according to the observer's point of view. Now, because this is a two-dimensional vector, we do have to find the angle and the final direction. So using tan inverse and then the tips of tails notation, we're going to get the angle and final direction here. And that would make our resultant vector 2.06 meters per second, 29 degrees east of north. Now for part B, when it asks how long would it take the swimmer to reach to the other side of the bank, we only want to use the speed or the velocity that is actually going to take us to that other side of the bank. If I use the resultant speed or velocity, that's going to take us diagonally reference to the bank. And if I take the river current, well, that is going to only take us east. So between the three speeds or velocities given here, only the 1.8 meters per second is actually going to get us to that other side. So whenever you're dealing with relative velocity questions that ask you, how long would it take to get to this certain place, you would only ever choose the velocity that actually takes you directionally to that certain place. In this case, that is the northern arrow of 1.8 meters per second. And when we calculate that, we get 111 seconds it takes to get from the south bank to the north. Now, for part C, where we want to know how far downstream, remember that downstream just means horizontally. So in this case, the only horizontal vector is the eastern vector. So similar to part B, we're only going to choose the velocity that actually takes us in that direction. So when I plug in my formula, D is equal to V times T, then I have to keep in mind that I must only use the velocity that actually takes me there, which is 1.0 meters per second east. And then multiplying by these seconds, which I counted in or calculated in part B, that gives us 111 meters downstream.